Swarm systems consider the propagation of local interactions in a communication network in order to express a global behavior like reaching a goal. A swarm controller encodes the way individuals interact locally. We formalize a communication network as a weighted and directed graph. We use Delaunay triangulation to get all particles nearest neighbors and then track edges to see for how long they exist. We apply dynamic time warping to get a distance between two position trajectories. The difference between the warping curve and the diagonal that represents a perfect match is used to obtain the interaction magnitude between two individuals. A particle follows another one inside the half plane defined by its orientation vector. The closest particle in terms of orientation angle is the one ahead. With the following information, we can build chains. Particles that occur often in leading positions have a higher magnitude of leadership. Simulations were carried out in Argos. Positions of individuals under different controllers, swarm sizes, scenarios, and communication ranges were recorded. Simulation time was 20 seconds. The controller Boyds is being simulated with 10 robots and 2 leaders. They are swarming towards the goal. To the left, we can see an inferred topology and a heat map of interactions. Orientations also gives us a clue of which robots are leading. Boyds tries to model how birds organize in a flock. For all samples, interaction magnitude and density distributions were analyzed to see if there was a relationship with swarm parameters. We can see that the interaction magnitude increases with the size when swarming around a point. Also, for goal-based scenarios, communication range increases with density, but only when it's lower than 300 centimeters. Morphogenesis is based on how cells organize themselves to create more complex structures. Density increases with size for all scenarios. The communication range did not have a clear influence on the distribution of interactions. Physical mimetics is based on the modeling of attraction and repulsion forces. Goal-based scenarios maintain a solid distribution above 0.8 no matter the size. Communication range seems to narrow the distribution to higher interaction values. Particle swarm optimization introduces a stochastic approach to explore a search space trying to optimize the fitness function. When swarming around a point, the interaction magnitude seems to increase with the swarm size. Communication range seems to narrow distributions to higher magnitudes, but there is no clear relationship. Leader detection was applied to flocking in physical mimetics controllers. 20% of individuals are leaders. The goal scenario shows 100% detection for all sizes. The same happens when obstacles are considered. Physical mimetics fails at 60 robots in the goal scenario, when accuracy falls to 75%. Obstacles have a much worse performance, dropping the accuracy to 67%. In conclusion, swarm local interactions can be represented in a topological graph, recording both orientations and interaction magnitudes. This is then used to infer leaders by using orientation data. Interaction magnitudes were used from a density distribution point of view. While it was found that such indicator was good to identify a swarm by size or scenario, global parameters like communication range did not have a clear relationship with distributions.